Hello, welcome to today's mini lecture on calculus. Our topic is a tool called logarithmic differentiation, used to differentiate certain functions that cannot be differentiated using any differentiation method used so far. Let me briefly review these other methods. We have sum rule for sums and difference rule for differences. For products, we use product rule, or if one of the factors is a constant, even the simpler constant multiple rule. For quotients, we have quotient rule, and for composed functions, we have chain rule. We use this chain rule for expressions of the type square root of an expression, or any radical of an expression, or logarithm of an expression. We also use chain rule for certain exponential expressions. For those with a fixed exponent and any expression as base, we use chain rule in combination with power rule. For exponential expressions with a fixed base and any exponent, we can also use chain rule in combination with rules for differentiating exponential functions. But what if we have to differentiate an exponential expression with both base and exponent expressions depending on x? An example is a function f of x equals x squared minus square root of x to the power of 2x plus 3, but also the much simpler looking function f of x equals x to the power of x. Note that these functions are not power functions, not exponential functions, not sums, not differences, not products, not quotients, not composed functions. None of our tools so far works. We need the method of logarithmic differentiation. This method has two parts. The first part is just the following advice. If you cannot differentiate a function, try to differentiate its logarithm. Instead of differentiating the function f, we try to differentiate another function g, defined by g of x equals ln of f of x. Although this sounds a little silly, a little like if you cannot do the calculus homework, watch your favorite TV show instead. It is not that silly, since the derivatives of f, the function we need to differentiate, and g, the function we should differentiate according to the logarithmic differentiation advice, are closely related. The function g is a composed function with ln as an outer function and f as an inner function. Therefore, according to chain rule, the derivative of g prime of x, equals 1 over f of x times f prime of x. And that of course implies that f prime of x equals f of x times g prime of x. Meaning that if we have g prime, we also have f prime. This relation between f prime and g prime is the second part of the logarithmic differentiation method. Now g of x looks even more complex than f of x. Why can we differentiate this more complicated looking function if we cannot differentiate f of x? But keep in mind that we are interested in very special functions f, exponential expressions. And remember that the logarithm of an exponential expression equals the exponent times the logarithm of the base. This is one of the laws of logarithm. So g of x is a product of the former exponent and the logarithm of the former base. So we can use a combination of product rule and chain rule, used for the second factor to differentiate the new function g. Let's now look at the example f of x equals x to the power of x. We get g of x equals ln of x to the power of x, which equals g of x equals x times ln of x. This function is fairly easy to differentiate. Using product rule, we get g prime of x equals x times 1 over x plus 1 times ln of x, which is just equal to 1 plus ln of x. Therefore, f prime of x equals f of x times g prime of x, which is x to the power of x times 1 plus ln of x. Of course, this was the simplest possible example, For a more complex example, let's take f of x equals x squared minus square root of x to the power of 2x plus 3. We follow the advice given by the first part of the logarithmic differentiation method and introduce the function g of x equals ln of f of x, which is the ln of this expression, which simplifies to g of x equals 2x plus 3 times ln of x squared minus square root of x. So we have a product. The first factor is easy to differentiate. For the second factor, ln of x squared minus square root of x, we have to use chain rule. So we differentiate and get g prime of x equals 2x plus 3, which is a copy of the left factor, times 1 over x squared minus square root of x, which is the autoderivative of the right factor, times 2x minus 1 over 2 times square root of x, which is the inner derivative of the right factor, plus 2, the derivative of the left factor, times ln of x squared minus square root of x, which is just a copy of the right factor. Therefore, f prime of x equals f of x times g prime of x, so we get this rather lengthy expression here. Let me close with two remarks. First, logarithmic differentiation is often also used in cases where we don't absolutely have to use it, since we could also use other methods, let's say product rule or chain rule. An example is f of x equals 2x plus 1 to the power of 3 times 3x squared plus x to the power of 4 times 4x minus 1 to the power of 5. Well, a product of these three parts. Of course, we could differentiate this function by applying product rule twice and also applying chain rule, but this is a rather lengthy procedure. We could also instead use our logarithmic differentiation method and introduce g of x equals ln of f of x. Since the logarithm of a product equals the sum of the logarithms of the factors, we get g of x equals 3 times ln of 2x plus 1 plus 4 times ln of 3x squared plus x plus 5 times ln of 4x minus 1. This sum is easy to differentiate using sum rule and chain rules. We get g prime of x equals 3 times 1 over 2x plus 1 times 2 plus 4 times 1 over 3x squared plus x times 6x plus 1 plus 5 times 1 over 4x minus 1 times 4. Therefore, f prime of x is just the product of f of x and g prime of x, which is this lengthy expression spanning two lines. And the second and final remark is that all these laws together, including the logarithmic differentiation method, we are now able to differentiate any function that is defined by an expression.